Hello friends, in the last video we have seen the consolidation process where you have seen that the saturated clay soil mass, when it is loaded, the extra load goes to the pore water of the saturated clay soil mass. As a result, excess pore water pressure builds up. And this excess pore water pressure is going to dissipate over a longer period of time because of lower permeability of the clay soil mass. Because the hydraulic conductivity of the clay soil mass is quite less, it takes longer period of time. And therefore, the loaded soil mass goes under consolidation after dissipation of the pore water. As the pore water dissipates over a period of time, the soil is going to rearrange itself, the void is going to decrease, and therefore leading to settlement. And its application in any civil engineering structures where whether it is a foundation or any other structure where the load from superstructure goes to the footing, you will find that the settlement of the soil mass leads to the settlement of the foundation. Therefore, the consolidation process and consolidation settlement is very, very important. So, last time we have seen that there is a saturated soil mass. So, any soil mass which is saturated clay soil. Now, this saturated clay soil, if you are going to apply the additional load, this additional load will induce stress at any point. So, additional stress is going to be in picture because of this additional loading at the level of the surface or at the level of the footing. So here there is going to be increase in the stress mass, and that is called delta sigma prime. So there is going to be, due to the additional loading from the footing, there is going to be at any point, whether you consider this point as A, there is going to be increase in stress. So this is called increase in effective stress. And this point A is, say, at a depth Z from the surface, then at this point the overburden pressure, the effective overburden pressure is going to be effective unit weight of the soil mass multiplied by Z. So already this was existing. The moment the pore water pressure, the total pressure, sigma T is going to be this effective pressure plus the pore water pressure, which is acting in the upward direction. The excess pore water pressure that is getting built up because of this additional load. And this is going to decrease over a passage of time. That is going to, the liquid or the water in the void is going to come out from this soil mass. As a result, the void ratio is going to decrease. So the effective pressure is going to be total pressure minus excess pore water pressure. This excess pore water pressure is going to dissipate over a period of time, And therefore, once it dissipates, this excess pore water pressure becomes 0, and this additional loading comes to the soil mass, soil skeleton, and the effective stress is going to increase. So this will increase once it becomes 0. So the total stress which has been applied on the surface will be coming to the soil skeleton. So the dissipation of the pore water, because in the three-phase diagram, we know that the saturated soil mass is going to be composed of the soil solids, the volume of the soil solids, and the void which is completely filled with water. And therefore, it becomes fully saturated clay. And this is the total void which is filled with water, isn't it? Now, once you are going to apply the additional this, there will be reduction in its volume. So the figure will look like this. The water will dissipate, the excess pore water pressure will dissipate, and therefore you find that there is going to be reduction in the void by delta E, leading to consolidation settlement. So consolidation settlement is because of dissipation of this pore water. So once this pore water goes out of the system, it leads to reduction in the void and it leads to consolidation settlements. But it takes quite a longer period of time. Sometimes it may take more than a year, more than 2 years, 3 years. So depending upon the hydraulic conductivity of the soil mass, gradually this excess pore water pressure, because of the additional loading that gets developed, the excess pore water pressure is going to dissipate, leading to reduction in this. So if you plot it, this reduction of what is the increase here is delta sigma prime. So if we plot here the increase in effective stress sigma prime, and here on the y-axis if it is the void ratio, then you will find that once the soil mass is subjected to additional pressure, what is going to happen is that there is going to be a reduction in the volume of the soil mass. And as the pressure increases, you will find the void ratio decreases, and it gets flattened after certain period of time. So if this is the graph where it is sigma prime, that is effective stress, versus void ratio E plot. And for any pressure range, let's say I take this pressure range. This is the pressure range, if this is the point 1 and this is the point 2, then here it is sigma 1 prime is sigma 2 prime. So sigma 2 prime minus sigma 1 prime is going to be delta sigma prime. So sigma 2 prime minus sigma 1 prime, that is the difference in the effective stress, is going to be delta sigma prime, and the corresponding void ratio, let's say it is E1, and here corresponding to sigma 2 prime it is E2, where E2 is less than E1. This gives you the E2, E1 minus E2 will give you delta E. So For any pressure range from sigma 1 to sigma 2 prime, you can find it out that a coefficient known as coefficient of compressibility. So, a coefficient of compressibility is uh, given by symbol AV, which is equal to delta E divided by delta sigma prime. And because the void ratio is going to decrease, you can take a negative sign over here. So a coefficient of compressibility is the decrease in void ratio of the saturated clay soil mass for corresponding increase in effective stress in the soil mass. So this term is very important that we should know about it. There is another term known as coefficient of volume compressibility. So coefficient of volume compressibility, we call it MV. So MV is going to be the change in the volume upon original volume. Say this is the soil mass. It has got the original volume as V naught, and the change in the volume, if it is laterally confined, because we are going to talk about one-dimensional consolidation, the saturated clay soil mass is going to settle only in the vertical direction because it is laterally confined, and therefore we can say this delta V equal to delta H, and this is H naught. We can write it like this. So change in volume per unit volume per unit increase in pressure. So what is the increase in pressure per unit increase in effective pressure is called coefficient of volume compressibility. Or in other words, we can say this coefficient of volume compressibility for one-dimensional consolidation, delta V will be given by the height, which will be total height will be H naught. So this is going to be the total height, original height, H naught, and that is this is going to be the change in the height. So this is going to be delta H, and this is going to be delta sigma prime, the increase in the effective stress. So we can write it, this is minus delta H divided by H naught into 1 plus 1 upon delta sigma prime. This is called the coefficient of volume compressibility. Now you know that delta H equal to delta E. So delta E divided by this delta sigma prime is going to be equal to AV. So it can be also an H naught equal to 1 plus E naught, because Vs is taken as unity from three-phase diagram, and therefore total H naught becomes 1 plus E naught. Therefore, this MB can also be written in this form, because you are all conversant with three-phase diagram. This MB can be written as AV divided by 1 plus E naught, because this delta H equal to delta E. So delta E divided by delta sigma prime is going to be AV, and H naught is going to be 1 plus E naught, and therefore it can be written as AV divided by 1 plus E naught. But you see, it is for a particular pressure range. As the pressure range is going to change from sigma 2 to sigma 3 prime, now between sigma 2 and sigma 3 prime, the value of both AV and MV will change. So it is specific to pressure range. For sigma 1 to sigma 2 prime, the value of AV and MV are going to be different. For the pressure range of sigma 1 prime to sigma 3 prime, the value of AV and MV will be different. For value of sigma 2 prime to sigma 3 prime, the value of AV and MV will be different. So it is a subjective, it is a unique value, and therefore for a particular pressure range. So pressure range is very important over here. And therefore, in the last video, I had told you that if you are going to plot it on a logarithmic scale, now let's say I am going to have this effective stress is plotted on logarithmic scale, and this void ratio is going to be on arithmetic scale. That is, you take a semi-log paper and plot it, you get a virgin curve like this. Now, if it is normally consolidated soil, you will be getting a straight line. Now the question is, what is normally consolidated soil? A soil mass here which has not been subjected to a pressure greater than the present pressure is called normally consolidated soil. So for normally consolidated soil, in the stress history, this has not been subjected to. So this is called a virgin curve. So this is the virgin compression curve. And if its slope, if you take it, this slope is going to be delta E, change in void ratio for a pressure range for if this is 0.1, this is 0.2, this is sigma 1 prime, this is sigma 2 prime. Therefore, you get the slope of this line, virgin compression curve, for normally consolidated soil, you get therefore, for normally consolidated saturated clay soil, what we get it? This slope of this line is called compression curve. So you get compression curve, CC. So CC equal to delta E divided by log of, because it's on log scale, sigma 2 prime minus log of sigma 1 prime. So we can also write it, this is equal to delta E divided by delta log of sigma 2 prime divided by sigma 1 prime. So this is very important. Now, you see, if the soil has been already subjected to very high pressure in the past, say the ground has been subjected to a very high pressure in the past. So if the stress history is as such that in the past there was a monument or some structure already existing, which is not existing today, that means the soil in the past has been subjected to a very high pressure. But the structure doesn't exist today. Or there was a glacier falling from a certain height, and due to impact, the soil mass has been subjected to very high intensity of stresses in the past, then it will behave as a pre-consolidated soil. It will not behave like normally consolidated soil. In normally consolidated soil, in the past, the soil has never been subjected to any intensity of loading higher than the present pressure. But over consolidated soil means, or pre-consolidated soil, it has been subjected to higher amount of pressure in the past, but the present pressure is lower than that pressure, then the behavior will not be like this. So we have got Normally consolidated soil. Now, for pre-consolidated, or it is called over-consolidated soil. That means this soil has been subjected to higher stresses in the past than the present pressure. Whereas here, the present pressure for normally consolidated soil, which we call it NC soil also, normally consolidated soil. For NC soil, the present pressure is the highest. It has not been subjected to a pressure greater than the present pressure. So the present pressure is the highest in its stress history. In its stress history. Then it is normally consolidated. But here, as I told you, that if there was any reason, whether there was a monument which is not existing today, say today Taj Mahal is there after few centuries, if it is not there, then that soil will behave differently. That clay will behave differently. It will behave like pre-consolidated or over-consolidated soil. It is also called OC clay, over-consolidated clay. So normally we have got NC clay, we have got OC clay. Now the behavior of OC clay, if you see, is different. It's not. So here, on the logarithmic scale, when you plot it, it becomes a curvilinear one like this, and then it becomes a straight line. It becomes a straight line. So it is something like this. So here, in the last video, I have told you that how to find out pre-consolidation pressure. You have to find out a point O which has got minimum radius, R minimum radius, where you are going to have a horizontal line. So it becomes OA, right? And then what you are going to do is draw a tangent over here. So this becomes the tangent, isn't it? Let's say this is B. So AOB is then divided. So this is the bisector of AOB, and then this straight portion, when you extend it in the backward direction, this intersect this bisector at certain point, and this pressure is called pre-consolidation pressure. So this is pre-consolidation pressure. Now, what you find? It is curvilinear. That means it is more steeper. It is flatter. So before pre-consolidation pressure, it is going to behave as OC clay, over-consolidated. That means there is the pressure which has been already pre-consolidation pressure. Your soil has been subjected to this amount of pressure in the past. So your present pressure may be less than this pre-consolidation pressure. So what you are applying is somewhere here at point 1, which is sigma 1 prime. Now sigma 1 prime is quite less than the sigma p prime. but the soil in the past has been subjected to sigma p prime. Therefore, it will behave like over consolidated clay. It is, and to find out this is very, very important. So you need to carry out the test, consolidation test, and you will have to plot this void ratio versus for the given value of the effective pressure over the soil mass. So if you take a soil sample and apply the effective pressure, so you apply the effective pressure, sigma 1 prime, sigma 2 prime, and find out the corresponding void ratio. And if it is normally consolidated, then you are going to get a straight line. Otherwise, you will be, if it is a normally consolidated, otherwise you are going to have a, for over consolidated soil, the nature of the curve is going to be curvilinear, and then it is going to be straight one. So while computing the settlement, you will find here the CC value, the compression index, is quite high compared to the slope of the part before pre-consolidation pressure. So in how to compute the settlement of over-consolidated clay, that is the mute question that I will discuss in my next video. I hope I have explained the concept of normally consolidated and pre-consolidated soil. The soil could be under-consolidated also. So these are the different conditions of the clay soil mass which I have explained to you, and I will be explaining further how to compute the settlement of normally consolidated soil, how to compute the settlement of pre-consolidated soil using the compression index. So this compression CC is called compression index. So this is the compression index CC. Now, if it is over consolidated soil, you can see that if you plot it here, let's say you are having sigma prime, and here it is void ratio, and the sample is subjected to this additional effective pressure, then it is going to decrease like this, isn't it? The void ratio is going to decrease as the effective stress increases. Now, if you reload it, it goes like this. Unload it. So this is the part of unloading. Now, if you reload it, it will come to this point, and then it becomes further, it increases, further it goes like this, isn't it? So E versus sigma prime, or sigma prime versus E, is going to be like this. So here the average value of this will give you a index, and that index is called the recompression index. Here you are going to recompress the soil. So here it is reloading or recompression or recompression. Same thing if you plot it on a semi-log paper. So log sigma prime, here the void ratio. What will happen? That it is going to be like this. And then here you have come to this point A, and then you are going like this, back, reloading, unloading, and then if you reload it, you will be getting like this. And then once you come to this point A, and later on, if you increase the effective stress, you are going to be like this. So this is called the virgin curve. And this is called unloading, this is called reloading, and the average, its slope will give you the value of Cc, and this recompression uh, curve will be the slope of this one. Now recompression is index is going to be much less than compression index because it is more steeper, whereas this is flatter. This is a flatter one. Therefore, the slope of this line is going to be recompression index. So CR is called recompression index, which shows that the soil has been already subjected to a stress uh, of sigma A prime. And once you unload it, you go to the point B. Now, once you reload it, then it becomes over consolidated because the soil has been already subjected to this particular pressure. Now, the what pressure you are applying here is less than the pressure already applied. So when you are going to reload it, it is going to behave like over consolidated soil. So this is the part in which it will behave. This is the part in behave like OC clay. So OC clay, you will have to find out the recompression index, and recompression index and compression index. As I told you, the compression index is going to be much higher, and recompression index is almost 10%, 7 to 12% range, it varies. So CR is going to be 7 to 12% of CC value, quite less. Average you can take it 10% of CC because you see the nature. So in over-consolidated clay, where the soil has been already subjected to higher pressure, you will have to consider this recompression index. Whereas for normally consolidated, you will have to use compression index and then compute the settlement. The settlement for over-consolidated part will be quite less, and therefore CR is quite less. This I will explain to you in the next video. Thank you very much.